Today we define positive semi-definite and positive definite operators. Learn practical checks. And see why positive definite matrices define inner products and norms no ellipses today. We are pretending restraint is possible. We start with a self-adjoint operator A. For a real matrix, that means symmetric. Without this assumption, the phrase positive definite becomes a trap with notation on it. A is positive semi-definite if inner product of AX with X is always non-negative. The value is allowed to be 0 for non-zero vectors. A is positive definite if inner product of AX with X is strictly positive for every non-zero X. Positive definite forbids flat directions. Semi-definite politely lets them loiter. For real matrices, the expression is X transpose AX. This is a quadratic form, which is basically a function that measures squared length after the matrix has tampered with reality. The diagonal matrix with entries 2 and 1 is positive definite, because every non-zero vector gives a positive value. Shockingly civilized. The diagonal matrix with entries 1 and 0 is only semi-definite. The non-zero vector 0, 1 still gives value 0. That is a flat direction. The diagonal matrix with entries 1 and -1 is not semi-definite. Because the quadratic form can be negative, the measuring stick has become hostile. The cleanest check uses eigenvalues. For a self-adjoint operator, positive semi-definite means all eigenvalues are non-negative, and positive definite means all eigenvalues are positive. Here is the proof. By the spectral theorem, choose an orthonormal basis of eigenvectors. Write X as C1e1 plus plus CNEN. Then inner product of AX with X becomes the sum of lambda I times absolute value of Ci squared. If every lambda I is positive, every non-zero X gives a positive sum. If one eigenvalue is negative, use its eigenvector and the quadratic form is negative. If one eigenvalue is 0, use its eigenvector and positive definiteness fails. The matrix confesses immediately. For a 2 by 2 symmetric matrix, there is a useful shortcut. A is positive definite exactly when A is positive and AC minus B squared is positive. This is not magic, it is just completing the square, which is algebra's way of pretending it had a plan all along. If A is positive and AC minus B squared is positive, then both squared terms have positive coefficients. So every non-zero vector gives a positive value. Conversely, if A is positive definite, plugging in 1 0 shows A is positive. Then the same completed square forces C minus B squared over A to be positive. So the determinant is positive. Now suppose A is positive definite. Define a new inner product by inserting A into the first slot. Inner product of X and Y with subscript A equals inner product of AX and Y. For real matrices, this is X transpose AY. It is the ordinary dot product. Except A has changed what the measuring stick means. Very modest of it. Linearity follows from linearity of A and linearity of the old inner product. So far, no sorcery, despite appearances. Conjugate symmetry follows from a being self-adjoint. That is exactly why we demanded symmetry at the start instead of just hoping for the best. Strict positivity follows from positive definiteness. This is the part semi-definite matrices cannot guarantee, because flat directions keep freeloading. Every inner product gives a norm, so define the A norm of X as the square root of X transpose AX. If A is only semi-definite, this can fail to be a norm. For the diagonal matrix 1 0, The non-zero vector 0, 1 has a length 0. A non-zero vector with 0 length is not a norm. It is a mathematical complaint waiting to be filed. Positive definite avoids that mess. Positive semi-definite means the quadratic form is always non-negative. Positive definite means it is strictly positive on every non-zero vector. For self-adjoint matrices, eigenvalues give the main test, and symmetric positive definite matrices define inner products and norms next time. Cholesky decomposition factors them into something easier to compute with.